Jaipur as another special guest of the evening. On virtual mode, we are honored to have the presence of Dr. T.M. Gunaraja, past President IEI, Dr. G. Raghunath Sir, Chairman CATEIEI. We have among us Dr. Sriram Satyanarayana, Chairman, Production Engineering Division, IEI. In this program, we also have Mr. Sandeep Kumar Ghosh as a speaker. He's a Deputy Manager, R&D and Project Management, Tata Motors Limited. We have Dr. Saurav Datta, Associate Professor in the Department of Mechanical Engineering, NIT Rourkela. He's our another expert speaker. We have among us Dr. John Deburma, Associate Professor, Department of Mechanical Engineering, NIT Agartala, as our another speaker. We have Dr. Shubhadeep Bhattacharjee, Honorary Secretary, IEI Tripura State Center. We have Engineer Shujoy Kaur, Organizing Secretary. I also welcome the students of NIT Agartala. Now, without making any further delay, I would like to request Engineer A. Anbarasan, Managing Director, Tripura Natural Gas Company Limited, Engineer Bishwajit Deburma, Engineer Sanjay Garwal, to kindly grace the dais. Please, sir, you are kindly requested to take your seats on the dais. I also request Dr. Shubhadeep Bhattacharjee and Engineer Chinmoy Devnath, sir, to kindly take their seats on the dais. Welcome you all. Now, I would like to request Engineer Chinmoy Devnath, sir, Chairman, IEI Tripura State Center, to welcome Engineer A. Anbarasan, Managing Director, Tripura Natural Gas Company Limited, and also the chief guest of this session with the memento. Thank you, sir. Thank you so much. Now, Engineer Bishwajit Deburma, sir, General Manager, Gas Authority of India Limited, as a special guest of this evening. Now, I would like to request Engineer Chinmoy Devnath, sir, to give the welcome address. Please, sir.
Good afternoon, respected past President of the Institution of Engineers India, Chairman KATE IEI, Chairman Production Engineering Division Board IEI, the today's chief guest in this program, Engineer A. Anbarasan, Managing Director, Tripura Natural Gas Company Limited, the special guest, Engineer Bishwajit Deburma, General Manager, Gas Authority India Limited, Agartala. In our today's program, Engineer Sanjay Garwal, Vice President, OTPC Limited, Palatuna, was supposed to be present, but due to some urgent meeting with his headquarters in Delhi, he couldn't come till now. Our speaker on this occasion, Dr. Saurav Datta, Mr. Sandeep Kumar Ghosh, Dr. John Deburma, Honorary Secretary of our center, Dr. Shubhadeep Bhattacharjee, the Organizing Secretary, the Committee Member for Mechanical Engineering Division, the Moderator, the faculty members, the participants, and my beloved engineering students. In connection with this 32nd Foundation Day of the Institution of Engineers India Tripura State Center, we are conducting one-day seminar of various engineering division. Today is the 5th day, and today's one-day seminar is on advances in production engineering, being organized by the Institution of Engineers India Tripura State Center under the aegis of Production Engineering Division Board IEI, jointly with Department of Production Engineering NIT Agartala, Department of Mechanical Engineering NIT Agartala, and Department of Mechanical Engineering, Tripura Institute of Technology. And in this program, I would like to take the privilege to welcome all of you. As you know that the Institution of Engineers India Tripura State Center, including its the period of local center, Agartala local center, have completed 32 years. And 1st April is our foundation day. So in this connection, we have decided to celebrate this program. So this program. Along with inaugural closing ceremony and also our general discussion along with cultural program and 5 one-day program of civil engineering, electrical engineering, production engineering, electronics engineering and chemical engineering. So today is the 5th day. I am really happy to welcome our first chairman, the very dynamic person, Dr. T.M. Gunaraja ji, who is from Chennai, and on our invitation, he has been agreed to grace this occasion, and we shall be eagerly waiting to hear from him, who is also a well-wisher of our center. In fact, our skill development floor was inaugurated by him, and with his best wishes, it was possible for us to complete. And I hope in future days also we shall be getting support and guidance from Gunaraja ji. The technical activity of Institution of Engineers are being monitored by the CATE only, and the chairman of this CATE of IEI is Dr. G. Ranganath. I specially welcome you, sir, in our
Good evening, sir.
In fact, your guidance and involvement encourage us to conduct such type of technical activity, and in future days also we shall be taking your support and guidance to conduct our technical activity in a befitting manner. Dr. Sriram Satyanarayana ji, the chairman of Production Engineering Division, who is the key person to give permission to our center to conduct this one-day seminar on advances in Production Engineering Division under the aegis of Production Engineering Division Board. I especially welcome you, sir, and the way you have given clearance to us to organize this program. In future days also, we shall be looking forward to get such type of guidance and support. I am really happy to welcome Engineer A. Anbarasan ji, the Managing Director, Tripura Natural Gas Company Limited, who is present here as chief guest. In spite of his some busy program, he could manage to come, as he told, and I believe that it is his attachment and feeling for the Institution of Engineers, as we were getting earlier days also in our technical activity. And I hope in today's program we shall be listening from him, and for future program also we shall be moving together with TNGC Limited in regards to technical activity as well as in other matters also. I welcome Engineer Bishwajit Debarma, General Manager, GAIL India Limited, who is a special guest in our today's program. The GAIL Authority of India Limited, Tripura's chapter, they are supporting us in regards to technical activity in many years, and I hope in future days also we shall be moving together. And today the engineering students will be immensely benefited through his deliberation with his practical experience in the field. I welcome Mr. Sandeep Kumar Ghosh, Deputy General Manager, R&D and Projects Management, Tata Motors Limited, who will be presenting his paper through online, and it will be an educative one, which will be must immensely beneficial for the engineers, and they may participate in the interactive session also after the presentation. I am really happy to welcome Dr. Saurabh Datta, Associate Professor, Department of Mechanical Engineering, NIT Rourkela, who will be delivering lecture on engineering application of auxiliary metamaterial cellular structures, fabrication through additive manufacturing, and he will also be delivering his lecture online. Our third speaker is Dr. John Debborma, who is Associate Professor, Department of Mechanical Engineering, NIT Agartala, will be giving a presentation on friction stir welding of thermoplastics using a novel self-heated tool. I will be presenting this paper in this hall, and I hope the students will be very much lively after his deliberation. In our today's program, the Mechanical Engineering Division of our IEI Tripura State Center, the committee member Engineer Shivashish Bhattacharya is here, the organizing secretary Engineer Sujoy Kaur is here, and also the total program, the moderator are Dr. Sujoy Chakraborty, Assistant Professor, NIT Agartala, and also Engineer Pushparenu Bhattacharya from NIT Agartala. I welcome all of you in this program. I especially welcome our corporate members, the engineering students, and other invitees. As you know that the Institution of Engineers is doing a lot of technical activity throughout the year. And for information of our particularly engineering students, that we are conducting Saturday seminar for you, and you are presenting paper. There is a presentation from faculty also. And in this way, last year, in spite of this barrier from COVID pandemic, we could conduct around 65 programs during this 2021-22. And during our last council meeting in Hyderabad, we have seen in the record of headquarters, the total program as organized, the number, we are now in 3rd position in the country out of 125 centers. Though it is a small center, but it was possible as we are getting support from our corporate members, other fellows, the faculties, the engineering students of various technical institutes in our state. For kind information of our authority of headquarters, the center is conducting technical activity not in the institution building, but all part of the state, other district, other technical institute and technical organization also throughout the year, so that the organizations, the institute are involved in our activities, and through this thing, we are appealing the engineers serving in the, our state to take membership even for the student chapter activity also. So if we move together, I think one day will come when the Institution of Engineers India Tripura State Center may tell that the engineers who are serving in our state all are connected with the Institution of Engineers, the prestigious, largest engineering professional organization in the country. So with this, I once again welcome all of you, and I hope that today's 5th one-day seminar will be a grand success with the deliberation of the guests, the presentation of the speakers, and obviously interaction by the participants, maybe online or offline, and especially by the engineering students. So thank you very much, and with the hope that in coming days also we shall do such type of technical activity in a befitting manner. Thank you very much.
Thank you, sir. Thank you so much for your beautiful welcome address. Now, I would like to request Engineer Shivashish Bhattacharya, Member, Mechanical Engineering Division, IEI, Tripura State Center, to deliver his speech.
Good evening. Today, we are very much fortunate enough to have with us a galaxy of engineering towering personalities and stalwarts. I, on behalf of Mechanical and Production Engineering Division, Institution of Engineers India, Tripura State Center, welcome you all, sir. In each and every month, on 5th day, we conduct committee meetings for Mechanical and Production Engineering Division at our state center at 6 p.m. without any fail. During COVID-19, we have conducted webinar in virtual mode. We got many reputed and renowned speakers over virtual mode. For the last year, 2021 and 22, we have conducted the webinar. I am just repeating all the themes. 2nd May 2021, 2nd May 2021, a webinar. One thing I have forgotten. During webinar, one presentation from faculty side and the other presentation from student side. So 2nd May 2021, we have conducted webinar. Engineer Shukanto Das, Assistant Professor, Mechanical Engineering Department, TIT. One paper he presented, performance study of an inclined bubbling fluidized bed dryer during Cassiola drying. And from student side, Engineer Abhiman Devnath, PhD scholar, Department of Production Engineering, NIT Agartala, presented multi-criteria decision making, a case study. On 3rd July 2021, webinar from faculty side, Engineer Pratik Shaha, Assistant Professor, Department of Engineering, Mechanical Engineering Department, Techno College of Engineering, presented effects of nanoparticle addition in diesel and diesel, biodiesel, ethanol blends on the performance and emission characteristics of a CI engine. From student side, Engineer Kelvin Alexander, MTech student from NIT, numerical study of boiling heat transfer enhancement using nanofluids. Then on 4th September, we have conducted a webinar. On 7th November 2021, we have conducted another webinar. On 2nd January 2022, we have conducted another webinar. And on a regular basis, we are conducting meetings, committee meetings, and webinar on odd month every first Saturday for mechanical. Thank you. Welcome you all.
Thank you, sir. Now, I would like to request Engineer Sujoy Kaur to present his presentation.
Good afternoon. Good afternoon, all. Respected guest and member of IEI, and ladies and gentlemen. It's a great privilege for me to introduce our speakers today, who are going to share their valuable thoughts, knowledge, and experience to us. We have many prominent speakers with us today. We have Dr. T.M. Gunaraja, past President, Institute of Engineers. He set off his academic career with the Institute of Engineers India with a degree in mechanical engineering, signed up to ME Production Engineering from Anna University, soon substituted with a master's degree in business administration, and tracking his doctoral research PhD. Engineer T.M. Gunaraja has been All India Council member for quite long time and member of Finance Committee. III shadowing numerous responsibilities, his efforts to the student society has crowned him with the meritorious Mechanical Engineering Award at the 19th National Mechanical Convention, IEI, on 19 September 2003. He is recipient of Technology Excellence Award presented by the former Prime Minister of India, H.D. Deve Gowda, Indian Technology Awards 2014, Bharat Vidya Srimani Award by the International Institute of Education and Management, February 2015. We have Dr. G. Ranganath, Chairman, Kate, Institute of Engineers. He is working as a principal, Adhiyaman College of Engineering since 2008. He obtained his BE, ME, PhD degree in mechanical engineering discipline. He has over 34 years of versatile interdisciplinary professional experience and has published over 100 technical research articles in reputed national and international journals and conferences. He is author of 10 books on engineering and technology. Presently, he is serving as a syndicate member of Anna University, Chennai, and also served as a syndicate member and senate member of Periyar University, Salem. Our next speaker is Dr. Sri Ram Satyanarayana, Chairman, Production Engineering Division Board, Institute of Engineers. Dr. S. Satyanarayana, Council Member and Chairman, PRDB, is the past chairman, Institution of Engineers India, Telangana State Center. He served as a principal director, CEO, Central Institute of Tool Design, CITD, MSME, Government of India, and worked as principal and professor of engineering colleges, Hyderabad. He has worked in many prestigious organizations of the country. Presently, he is the director of an industry in Hyderabad manufacturing critical components and assemblies to defense and aerospace industries. We have Engineer A. Anvarasan, Managing Director, Tripura Natural Gas Company Limited. He graduated with B. Mechanical from University of Madras, ME Mechanical from National Institute of Technology, Surat, and MBA Marketing from Hyderabad. He has 34 plus years of experience in handling multifarious assignments in natural gas sector, covering diverse functions like construction, operation, and maintenance of natural gas, compressor stations, LPG pipeline, and pumping station. Before joining TNGCL, Engineer A. Anvarasan has been heading the operation of 1,180 kilometer DBPL pipeline construction in Karnataka, Maharashtra, and Goa states, and routed DBPL Private Limited. Engineer A. Anvarasan is now the managing director on the board of Tripura Natural Gas Company Limited, TNGCL, with effect from 21st June 2021. We have Engineer Sanjay Garwal, Vice President OTPC, Palatana Project, Udaipur. He recently joined in the OTPC organization. We have Engineer Bishwajit Deborma, General Manager, GAIL, India. We have Engineer Sandeep Kumar Ghosh, Deputy General Manager, R&D and Project Management, Tata Motors Limited. He has more than 9 years of experience in research and development as DGM of biggest project of Tata Motors, Tata Prima Vehicles. He had taken active role in training, development, supervision as team member, extended technical support for smooth product launch. He has traveled extensively across the globe like Russia, South Africa, and Middle East to identify the customer needs and configure products according for those markets. He has 3 patents. We have Dr. Saurabh Dotto, Associate Professor, Department of Mechanical Engineering, National Institute of Technology, Rourkela, India. Dr. Saurabh Dotto is an Associate Professor in the Department of Mechanical Engineering of NIT Rourkela. He has guided more than 12 PhD scholars and many MTech students. Dr. Dotto has published articles in many reputed international journals and conferences. He was selected as a highly commended award winner at the Literary Network Award for Excellence 2013 and was selected by the Emerald Group Publishing Limited UK Journals editorial team for the 2014 Outstanding Paper Award. We have Dr. John Deborma, Associate Professor, Department of Mechanical Engineering, National Institute of Technology, Girania. He has more than 20 years of experience in teaching and research. He has published many articles in reputed international journals and has presented papers in many national and international conferences. He has guided many PhD and MTech students. Dr. Deborma is also associated with many research projects and consultancy works. We are happy, very happy to see you all together here. Thank you all.
Thank you so much. Now, I would like to request Dr. Sriram Satyanarayana ji, Chairman, Production Engineering Division Board, IEI, to deliver his speech. Please, sir.
Thank you, madam. At the outset, let me congratulate the Tripura State Center for conducting so many technical activities. And being a small state, they have become the third state center in all over India in conducting the technical activities. I congratulate our Devana Sahab for his efforts, along with Dr. Subhadeep Bhattacharya, the Honorary Secretary. Today, this, Chairman of Tripura State Center, Engineer C. Devanandi, and Chief Guest of today's function, A. Anbarasan, and special guest, Biswajit Devabarma, and one more special guest, Engineer Sanjay Garwal, and our past President, Dr. T.M. Gunraja, Kate Chairman, Dr. G. Ranganatha Saab, Professor Sakhar Datta Saab, Engineer Sujay Kar Saab, Professor Sandeep Kumar Ghosh Saab, Dr. Saurav Datta, Dr. John Dev Burma, Dr. Sujay Chakravarti, Dr. Pushpa Renu Bhattacharjee, and all other participants of today's webinar. Namaste to all of you. When you talk of the production engineering is a very, very important topic you have selected, and production engineering is a very much required, so that the ideas whatever have been developed by R&D engineers and CAD/CAM engineers are to be brought into the real shape and put to the use for the community. Actually, if you talk of production engineering, it is a combination of various faculties of engineering, like mechanical engineering, manufacturing technology, engineering sciences, management sciences, metallurgy, and including hydraulics, pneumatics, electronics. All these things are put into the production engineering. It is really very, very a subject where a production engineer is supposed to understand all these things. When you talk of the advances, let us go, go back, to the very old times where, there was no interchangeable manufacturing. There is no interchangeability in manufacturing. The drawings were made, like art paper, and they used to know all the different parts of that particular assembly are marked with color codes. Today, all the color, the hatching and other cross lines, all these things have come. But in the olden days, they used to represent each parts by color codes. And similarly, the fitter is everything. They used to ask the fitter, this is my requirement. Fitter has to do, filing, scraping and grinding and whatnot things, and ultimately he has to assemble the component. And the components are not interchangeable. But it is during the 1800 year 1800, Ely Whitney, we have to always remember Ely Whitney as the father of the production engineering, because he has proved that interchangeability in manufacturing is possible. That is also, after 25 years of, James Watt brought out his more effective steam engine. It seems that James Watt struggled to bore that, engine to a very, very accuracy. And that is how the production engineers used to suffer like anything during that olden days. But today, there is a phenomenal progress in the development of machine tools. Production engineering goes with the machine tools, CNC machines or whatnot machine tools. So there is a phenomenal progress in the development of machine tools during the last 200 years. When you talk of the CNC machines, let us talk of the first generation CNC machines. First generation CNC machines, there used to be, one turret, and the turret is programmed. It used to do the boring, turning, and all sorts of things in the same machine by doing the programming. And similarly, if you talk of the CNC milling, it used to do all the functions only with the help of the single tool pattern. But in the second generation machines, what happened is the turret tools have been given, momentum, rotary movement, and they named it as CNC turning center instead of the CNC turning lathe. Then on the milling machine, the automatic tool changer has been added, and it can pick up the tools, different tools, as per the programming and as per the process requirement, and it will insert into the spindle, and it will start milling that. Then it has become the CNC machining center. Like there no CNC grinding center where you can do internal grinding and external grinding, all these things. But there are recent developments. Recent developments, if we take, this one middle turn technologies in Austria, they have developed a machine that is all what you call that, it can do everything. It can do convergence of dissimilar operations into a single machine. This machine can, do B-axis. The cutter head is incorporated the B-axis, and it can operate like, hard turning lathe. and 5-axis facility, machining facility, gun drilling facility, including 3D CMM facility. With this, all these things now the manufacturing has taken a very, rapid strides, and today we are able to produce anything that is required for an industry, and very effectively at a lesser time and more accurately. That was, that was the development that has taken over a period of time. And the manufacturing technologies have seen revolutionary changes for the last century. We used to call various manufacturing strategies we have seen, like mass production, lean manufacturing, flexible manufacturing, agile manufacturing. All these things have been introduced to improve the productivity, quality, cost, and variety. These strategies have been realized mostly by enabling technologies such like Internet of Things, advanced sensors, industrial big data, adaptive machine learning, cyber physical systems, etc. So when you talk of the emerging disruptive technologies, first thing what you have to talk is the 3D printing. Though it is rapid prototyping, earlier we used to call it as a rapid prototyping, now it has become a 3D printing. This rapid prototyping is a very old technology, but today, because we are able to center the metallic components with this 3D printing, so now it has become more versatile and more useful for the industry. And one more is the digital manufacturing. All of you are aware what is digital manufacturing. This traditional and experimental approaches to product development. Earlier, what you have to do when you have to make a prototype, we have to go for tooling and manufacturing one component, again analysis and putting for this use. All these things you have to do. But today, because of the digital technologies, all the traditional things have been overtaken, and now we can manufacture a component digitally in the laboratory, and we can make 3D modeling, manufacture the component, do analysis, all sorts of things. And once the component is okay, once the component is meeting all the requirements of the customer, then we can go for the real factory. This is the advantage of digital manufacturing. And today's one more very important this strategy is distributed cyber manufacturing. This distributed cyber manufacturing is really required because the manpower, we are facing a lot of problems with the manpower. There are experts available in some places, other places, other experts are available. To make use of all these things, the distributed cyber manufacturing is very much useful. For example, now some of the machines are fitted with modem facility. When the modem facility is available, you can download through internet all this data required for manufacturing the component or designing the component and directly machine the component. Or you can do a reverse engineering with 3D probes. And once this 3D probe collects all the data, it can generate, it can convert into a 3D model, and it can transfer to other place where you can take up the machining activity. So this kind of distributed cyber manufacturing has given a lot of advantage in the production area. And one more latest thing is these strategies enable the do-it-yourself manufacturing movement. Do-it-yourself manufacturing movement is very, very interesting because today we are able to book our flight tickets online. Similarly, the do-it-yourself manufacturing strategies, what they do is, there are some apps are coming. We need not go for the AutoCAD or maybe Solid Edge or Pro-E and other things. There are apps available. With the available apps, what we can do is, we can simply generate a 3D model, whatever we want, and with the help of the 3D printing, we can directly manufacture the component what we want. For example, I need a spectacle, frame. I can design with the app available with the app available, and I can print directly in the 3D printing. This is the advantage with the distributed cyber manufacturing strategies. And one more is hybrid process. Earlier, we used to subtract the material from the component used to manufacture. There is machining and other things. Today, it is additive manufacturing. Now, hybrid manufacturing, this hybrid manufacturing is able to use both the subtractive and additive manufacturing, including the macro, meso, including the electrochemical, thermal, mechanical, and optical. That is the multi-physics operations. This is the advantage of the hybrid process and multi-scale process. And today, everybody wants one-off component. Earlier, if it is a mass production, we used to go for various SPMs and transfer lanes and other things, and manufacture various jigs, tools, fixers. Today, everybody wants a different. Everybody, customer is very, very choosy. He wants a component having some features. Other customer wants some other features. All these things can be manufactured with this multi-scale manufacturing process. like micro machining or meso machining or nano, all these things. When you come to this nano manufacturing, I was reading this CIRP and some time back. The entire Encyclopedia Britannica can be micro etched on the head of a Alpine. So this is the greatest technology that is available today, the nanotechnology. And you need, that is the paper name is, I still remember, there is enough space at the bottom. In the paper, he says the entire, all the things, all the volumes of the encyclopedia can be written micro etched on a head of a Alpine. That means we can understand how much space is available, how much space we can save. This is how things are happening. And when you come to this manufacturing, one is manufacturing, then is the mission tools. In the mission tools, we used to have predictive maintenance and breakdown maintenance and all these the total productive maintenance, all these things used to come. Today, all the things are eliminated because the predictive analytics and infotronics for intelligent maintenance systems. These are, and one more thing is prognostics and health management for self-aware missions and equipment. It will analyze, because of the sensors that are inbuilt into the mission tool, it will analyze its health and it will communicate to the supervisor or the manager, this is my condition. Today, I need this oil to be changed, or I am already heated up. I need some rest. And this kind of technologies are coming up with the mission tools. With this, we are able to manufacture any type of component and any requirement that a customer wants, even is one-off component or a two-off components. That is one advantage. And one more thing, what is required is predictive manufacturing and smart factory. The one more is reconfigurable manufacturing systems. This is also very, very important. Today, this reconfigurable manufacturing is required because when product life is very often obsolescence has taken place, is becoming the order of the day. Very often the things are becoming obsolete. When the things are becoming obsolete, it is very difficult to throw it because of the environmental and pollution problems. So the reconfigurable manufacturing systems, what they are doing, when you are manufacturing the component product itself, you should think how to throw it and how to reuse it by changing some of the features. This is one reconfigurable manufacturing systems and the remanufacturing systems. This remanufacturing, today anybody is setting up an industry, he will invest a lot of money. Once he is investing crores of rupees, because of the obsolescence, the entire equipment is going waste. So in order to take care of the equipment, in order to change the equipment for producing some other things, there is one remanufacturing systems are coming into the society, and this is giving a lot of other advantages. And all of you are aware of smart industry 4.0, smart manufacturing, smart factories, all these things, and connected factories. I need not deal on this because this every is a buzzword. Industry 4.0 is a buzzword. Every one of us know what is Industry 4.0. With these few words, I am really happy that Tripura State Center has given me an opportunity to interact with all of you, and particularly the Honorary Secretary, Sri Sudeep Bhattacharya. He used to very often telephone to me and he used to ask whether you have received the link and other things. Thank you very much, sir, Sudeep Bhattacharya sir, and Devanar sir for giving me this opportunity. Thank you very much.
Thank you, sir. Thank you so much. Now, I would like to request Dr. G. Raghunathji, Chairman, CATEIEI, to deliver his presentation. Please, sir.
Here, Chinmay Devnath, Chairman of the Tripura State Center, Chief Guest, Engineer Anbarasan, Engineer Vishajit Deborma, Engineer Sanjay Agarwal, Past President, Engineer T.M. Gundarajaji, the Chairman of the Production Division Board, Past Chairman of Telangana State Center, good friend of me, Dr. Satyanarayana. Almost all he has become today a resource person for the program. You have seen how knowledge he is having, being is an industrialist, and is sharing a lot of experience and giving good tips as well. Engineer Bhattacharya, Honorary Secretary of Tripura State Center. Three eminent panelists Sandeep Kumar from Tata Motors, Professor Sarodatta from NIT Roorkee, Professor John Deb Burma from NIT Agartala, Professor Sanjay Chakrabarti, who is working as a moderator, who is taking responsibility as a moderator, and again is from NIT Agartala. All attendees from this wonderful program, let me extend my evening greetings to all of you. Good evening to all of you. Today, I am so happy to say that Tripura State Center, as our production chairman was telling, it was a small center, no doubt in that. But because of involvement, interest, and dedication by Chinmay Devnath ji and Bhattacharya ji, chairman and honorary secretary of the center, this Tripura State Center has become very vibrant today in entire country by seeing these programs from past couple of days, by celebrating their 32nd birthday. I am so happy to congratulate all the past chairmen, honorary secretaries of Tripura State Center, who have served from past 30 years, along with the committee members of various divisions, who made this center to travel all 3 decades very comfortably, conveniently. Because they made them to travel for 3 decades, today our Chinmay Devnath and Bhattacharya ji, they are given a different vibration to this center to see that it is going to have more visibility in the country in engineering fraternity, among engineering fraternity. Even I was on Saturday, I was at some time and I was attending some program civil engineering. So Devnath is bringing galaxy of resource persons from different divisions in every day. And even attendance also is very good. And today, if you take the speakers, as I told you already, Satyanarayana ji, as a chairman of Production Engineering Division Board, we can say he has given already technical talk. Rather than addressing as a chairman, he has given a technical talk by sharing his vast experience. Similarly, another 3 speakers are there. Apart of 3 speakers, 3 chief guests are there in the dais. So let me not touch on the topics of the production engineering, because everyone knows mechanical production, they both are one and the same. For want of this segregation has happened, that production has depended, but they cannot travel individually without depending on another one. It is everyone know it. But on this occasion, by congratulating Devnath and Bhattacharya ji, chairmen and honorary secretaries respectively, I am so happy to congratulate all of you. But my appeal today, all these are telling that small center, small state, small center, small state. This hurdle you want to come out. This ice you have to break means only one solution. You have to think of increasing your membership. Because there are a good number of institutions in and around your state, including NIT Agartala. There are a good number of teaching communities are available. And of course, there is a good number of students are doing master degrees in various disciplines in Agartala. So you can approach the respective deans and HODs of the institution and take them to the conference in the state centers and see that good number of memberships are going to be our additions to our state center, so that in the near years, one can say, though it is a small state in other way, but it is a big state in having a membership. That's what I want to appeal to Chairman Devnath ji and Bhattacharya ji. With this, I am so happy to say, any number of technical programs, apart from this 1 week programs, whatever our center is conducting, beyond this, good number of technical programs you can take forward. I am very happy from the IA side, will give all types of cooperation to you, coordination to you, as well. What are the best possible way we can help you in giving some seed money or financial support, whatever the way we can, it will be done for Tripura State Center conducting 32nd birthday. Devnath ji and Bhattacharya ji, thanks a lot for both of you for giving this wonderful opportunity. Thanks to our IAI technical departments coordinators, King Susan as well as Aparna, because they are showing a good interest. They are coordinating to the center. From beginning, I am observing they are coordinating as if they are the employees of Tripura State Center. I am so happy and thankful to them. That's why and that's how technical department of IE has to coordinate to every state center whenever technical programs are going to take place. So with this again, by congratulating the entire team of Tripura State Center, by thanking Chairman and Honorary Secretary, let me take leave of you. In some other occasion, I will join you. Thank you all, sir.
Thank you so much. Thank you very much for your beautiful speech. Now, may I request Dr. T.M. Gunaraja ji, past President, IEI, to present his speech.
Thank you, Madam.
Thank you, sir. Thank you, sir.
The Chairman Devnath ji, the galaxy of chief guests on the dais, the speakers, moderators, good afternoon to all of you. Tripura State Center is very close to my heart. When I was the president, the maximum number of visits made to a center mean that is Tripura State Center. Because the personal interest of each chairman for the development of center is excellent. Today, IEI technical webinar on advances in production engineering arranged by the Tripura State Center. I came to know that a series of lectures and All India seminars being going on last 5 days to commemorate the 32nd Foundation Day. In our stake at 123 state and local centers, any event, the first center come forward is Tripura. Similarly, today, coordinating all the divisions, organizing such a wonderful program, which can enlighten to all the students, academicians, and industries is appreciable. The purpose of the seminar by Tripura State Center is for the discussion which may help in bridging the gap in between the industry and academic institution. In fact, when I was a president, the Tripura State Center was focusing on skill development program. Even they were trying to tie up with the industries around, particularly the ONGC, to set up a skill development center. And to my best of my level, we also supported from IEI to construct a hall and motivate them to go for the continuous education program. So, though it's a small center, as everybody said, but the contribution to the society of engineering is great. The center has been making considerable effort to increase and diversify into many innovative areas. And I am happy to note that the center has succeeded eminently in its contribution to professional development of corporate members. It not only have the tie-up with the industries, it's also very much involved with the NITs to have many programs. I have also attended one of the convention that has created a good impact. The center has designed and carried out a range of technical educational programs in consultation with the reputed academician and the industry practitioners. It is also appreciative and encouraging to note that this takes great initiative to organize joint venture program with many state and local centers, particularly in the skill development area. I must congratulate Devnath ji for organizing such wonderful programs in all India basis. Particularly in this time, I would like to say the COVID has given a lot of damages to the human life, but it improved our digital learning system. That is what we are able to join all of us together in this convention. Otherwise, we may not give such an importance to these Zoom meetings or Google meeting. But now, particularly in IEI, whenever we organize, we all used to travel 2 days, 3 days to attend one seminar. But today, we are able to join all of us together in this digital platform is appreciable. At the outset, I would like to compliment Devnathji, as I said, particularly to bringing this program to enhance the linkages between academia and industry focus on synergistic outcomes. It is indeed in the fittings of things that this movement, as I would like to call, it has commenced in the Northeast, because in the Northeast only we have focused this program initially to go for the continuous programs. So that way Tripura is leading and doing good things. And as said, our CATE chairman, our production engineering division board chairman Satya Narayana is a well expert in production engineering. And in his address, he has highlighted many new things which is coming up in the production engineering. Though I am also a master's in production, but diversified into management now. But I'm happy to hear from Satya Narayana many things, the latest things which is happening in the globally. And I was like to focus on encouraging industry to enhance their participation in the institution activities at all our centers. That is happening now. In this context, I believe that it is the imperative that IEI evolves as a major platform for providing inputs for policy making in the engineering domain. This is what we had discussed in few of the division board meetings also. Whatever the seminars we or the conventions we make, there should be a policy making which has to go to the society to help. So that way, I expect Devnathji to take up this 5 days interdisciplinary divisions conventions and 1 day seminars to make up a policy and what we have arrived from all these experts and make it use to the Tripura state. Because we also tried to, when I was a president, we also tried to meet the politicians, the chief minister and everybody. And we were trying to help from all other states to Tripura State Center. I think that is happening. Devnathji can coordinate with the government to make all this policy making which we are discussing in this meeting to make it fruitful to the society. So with this, I wish this 1 day seminar to go very useful to all of us. And let's hear from the experts who have been gathered today to share their views. Thank you very much.
Thank you so much, sir. Now, with the permission from the dignitaries on the dais, there is little change in the schedule as per the urgent request of Mr. Sandeep Kumar Ghosh, Deputy General Manager, R&D and Project Management, Tata Motors Limited. Sir has got an urgent meeting, so we would have the presentation of Mr. Sandeep Kumar Ghosh, sir, now. So I will request Mr. Sandeep Kumar Ghosh, speaker of this session, one of the speaker of this session, to present his presentation. Please, sir.
Good evening or good afternoon to all of you. Hope I am audible to everyone.
Yes, sir.
If somebody can, yeah, thanks. So before I start my presentation, I would like to thank Mr. John and the Tripura State Center for inviting me and giving me the opportunity to present something on Tata Motors and something related what we are doing as a R&D center within the Tata Motors Limited. So I shall be presenting my screen. Just let me know someone that it is visible to everyone. And I am extremely sorry since at 5 o'clock I am having some urgent call. So that's why I asked Mr. John to change this time.
It's very clear.
Hope this my screen is visible to everyone.
Sir.
Yeah. Thanks. So before I start my presentation on my job profile and what as a ERC, as a Engineering Research Center we are doing, I would like to give some of the glimpses of what is Tata Motors and what are the different things Tata Motors or as a Tata organization we are doing. So I will start that as you all of know, Tata Motors is a global automobile manufacturer. It's a flagship. Tata Motors is a flagship organization. It is, and in 2008 we have acquired Jaguar Land Rover. In a commercial business scenario, we are the #1 player in the Tata Motors. And these are our various. Let me show the pointer also. These are our various products on a commercial vehicle, passenger cars, and a luxury vehicles. Jaguar Land Rover, Tata Daewoo, Tata Technologies, they are our key subsidiaries. And Fiat, Cummins, Marco Polo, BMW, they are our key strategic partners. So as you all know, we are a multi-billion-dollar company who sell from salt to software, actually. We are a company having a business starts from a very minute thing to very big things. So as a combined revenue of a Tata Group in last year, it was around $113 billion. And we are having a workforce of around more than 7 lakh all across the globe. And these are the various organizations within the Tata groups, which are very famous, like Tata Consultancy, Tata Steel, Tata Motors, Titan, etc. Regarding Tata Motors, where I am working, these are the various milestones. I will not explain each one of, but few of the milestones I would like to explain here. Like in 1945, Tata Motors started as selling engines, locomotive engines. And then in 1954, we migrated to commercial vehicle business. 2008, we acquired Jaguar Land Rover. And 2019, we launched Tata first EV vehicle in India. And the market share of this particular segment, Tata Motors is having almost 85% market share in EV presently. And we are the leading manufacturer in EV in India. These are the various countries where we are having our plants and the footprints, like UK, Europe, China, India, and North America. I am basically related with the commercial vehicle business unit, the research and development of a new generation vehicle. I am looking after it. So these are the various mission and vision of the things. So our main, Tata Motors' main mission is to provide a mobility solution to a common person so that his aspiration gets fulfilled. So this is our main mission, you can say, or a vision of the company. So these are the various commercial vehicles which are getting manufactured from various plants. I am basically looking after this particular product, MNSCV Prima, medium and heavy commercial vehicle Prima. So I joined Tata Motors in 2007. Myself and Mr. John, both of us did MTech. And prior to MTech, I did my BTech from NIT Nagpur. And then I did MTech along with Mr. John from Jadavpur University, Kolkata. So in 2007, I have joined Tata Motors, and thereafter, since joining, I was in R&D only. And I have, as it was already told, that I am having a very almost 14-year plus experience in R&D. And presently, I am a Deputy General Manager, and I am looking after the various commercial vehicle design and development things. So in today's presentation, a few of the key points I would like to explain how the things are going within the Tata Motors. So I'll start with the product concept. First, what we do, we generally conceptualize the product which we are going to launch. Then what are the technologies required into that product? We try to get that information through various QFDs. Post the conceptualization as well as by integration of key technologies, we build some of the prototypes in our plant and we do various kind of validations. Post validation, we also try to see what are upcoming trends in a near futures. So if those upcoming trends are known to us and it is viable for the product from commercial as well as from technological point of view, we try to incorporate those upcoming trends also into our products. And then finally, we launch certain product into the market. So I'll explain each one of things to certain example of whatever project I did in Tata Motors. So I am in a product concept year. So this is a kind of a vehicle which we have started as a new generation commercial vehicle. And this vehicle is basically to cater from 11 ton to 49 ton of load carrying capacity. And also this vehicle has to have a very high fuel efficiency as well as best operating economics so that whatever customer should purchase, they should get a high operating profit. To design such a new generation vehicle with all the different kind of engines, presently Euro 6 is going on. We have started at a Euro 3. We did a global benchmarking. We did a global benchmarking in South Korea, in Russia, in Middle East, that what kind of vehicle they are running and what are the things they did in their product. So almost we made around 600 plus customer, various application to be catered. Then we have captured the voice through a QFD, house of quality things. And with the help of our various engineering partners like WAPCO, Eaton, ZF, Bosch, we conceptualize a product. This is the concept phase of a product which we decided to launch in 2015 or 16 kind of thing. So various kind of cabins and all those things we try to incorporate. These are the basic pictures, what is there inside the vehicles. So once we finalize the concept, now the next thing is that we should have a product which is designed for next 20 years. Like, what can I say? Like if we are putting some kind of engine inside the vehicle, that vehicle can take from my smallest engine to a largest engine. So my design should in such a way that it should sustain at least 20 years of a product generation. So various configuration of engines and all those things we have did. Basically, these are what are the cabins, trim, features. So these all the things we did. So I will show one video. I don't know whether it is. So how my product is modular, that only by changing the tires and all those things, I can configure as many as product. I like to just. Let me know if this video is, if you can watch this video there. Is this video, are you able to see this video? Hello.
Yes, sir, we are able to see that.
Yeah. So I move to the other slide. Actually, basically, what I wanted to show in that video, that our design should be in a modular way so that we should be very quick to the market. Like I can give you one example in passenger car. You might have seen Tata Harrier vehicle. And then we have quickly launched Tata Safari. The only difference between the Tata Harrier and Tata Safari is that the at a rear portion, the length of Tata Safari is bit more than the Tata Harrier. So our product, however, we have changed many things into that Tata Safari. So our product should be designed in a such a way that it should be very modular and we should be very, very quick to the market. So now what I told, what are the different technologies, what we have incorporated into our product. Like earlier, if you have seen our commercial vehicles, the seats and the ergonomics was not up to that mark. So we have first time come up with this kind of pneumatic seat. It is like a car-like feeling. Then fully floated cabin. Presently, you have seen the cabin of a commercial vehicle, that's a fixed cabin. The drivers, the vibration of those cabin in such a way that drivers are complaining of for a back pain or something. So we have come up with fully suspended cabin. Then, as I told regarding the seat, so these are and totally aerodynamics cabin. So various kind of technologies we try to incorporate into our product. In presently, if you have seen the commercial vehicle, like unlike our car, they do not have, those vehicles do not have the air condition. We try to provide air condition into the commercial vehicle, the music systems. So all those things we are trying to provide as a new technologies. So post providing the technology and product concept, we build a prototypes. And before building a prototypes, some of the things we used to validate in a software like ANSYS, ADAMS, or whatever CAE softwares are available through that. And these are the various testing facilities like rig level testing, the software level of testing. So we are doing testing on our product so that our product once get launched, it should be a fault free or a complaint free. So whatever customer going to run the way customer going to run the vehicle, we try to simulate such thing in our test lab, and we do those kind of testing in our test lab before giving a product clearance. So the key technologies, as I said, we incorporated various kind of engine from smallest to the highest HP of engine, various gearboxes, 6-speed, 9-speed, 14-speed, the various axles, various kind of suspension on our product. So other than the key technologies, like you might have seen presently in many of the cars, we are presently saying our cars are connected. Means we can use a mobile app to switch on the AC. We can use our mobile app to find where is my car, or we can put some kind of geofencing or something. So those kind of technologies which are there in our car, since this commercial vehicle is of a next generation, we try to provide such kind of tracking or telematics devices in our product. As I said that almost before launching the vehicle, we need to do a rigorous validation. So almost 84 number of prototypes, 6.5 million lakh kilometer of highway testing, around 90,000 hours of hilly area testing. All those things we have extensively did. Also, we try to do many accelerated rig level of testing so that once our product gets launched, it should be a complaint free. So one more video I would like to show this kind of crash test. We are doing the crash testing. So there are many ads coming nowadays that Nexon is the safest vehicle. So we are pioneer in terms of safety and security for the customer. So not only in cars, but in our commercial vehicle as well. So various cold climate testing we do. These are the some of rig level testing, 8 poster kind of testing. So these are the various testing facility we are having. So post testing, one of our major criteria for a product is that it should have a very highly fuel efficient product, and it will provide a high cost of ownership. In fact, low cost of ownership to the customer. So this is a comparison between the Indian scenario and the European scenario. If we see here in India, the fuel cost, the percentage of spend by a customer on a fuel is around 52, whereas in Europe it's a 35. However, on a driver they are spending 40%. So for in Indian scenario, the foremost thing is how to save the fuel and increase the operating profit for the customer. So our main design prospect, or I can say a theme, is to save fuel. So we basically do many things to reduce the emission, as well as the consumption of fuel. So many technologies like aerodynamic things, optimized power cycle, the filling of fuel inside the engine. So all those things we basically do to change. This is basically one kind of fuel bubble chart I would like to explain here. Like if you see, these are the fuel bubbles. So, and this is the RPM. So engineering student might correlate this torque versus RPM graph. So if my fuel bubbles are here in this zone, so my vehicle will be much more fuel efficient. So at a lower RPM, at a lower torque, if my fuel bubbles are there, so it will provide a high fuel efficient vehicle. So these are the things we basically do while doing the validation. Now I'll go to the key mega trends which are impacting our commercial vehicle industry, like accident-free transportation, tolls regulation, the increasing competition, demographic changes and urbanization. The post-BJP government, the major focus is on the road and urbanization of cities. The total fleet transparency, like connectivity, as I said, the telematics and all those things. The upcoming technologies are this kind of automatic lane departure warning system, ABS, ABS. So this is autonomous. Now we are going ahead with the autonomous kind of thing, that where there will be no driver, however the braking and all those things will be done automatically. So it's a level 5 kind of thing. In India, it's a level, we are at a level 2, Europe is at a level 4. So we are inching towards that. So that's it from my side. If you have any question, some engineering students, you can connect me one-to-one, or you can ask me right now.
So we will have the question answer sessions at end of all the presentation.
Okay, sure.
Thank you, sir. Thank you so
Thanks.
much for your presentation. Now, I would like to request special guest of this program, Engineer Vishwajit Debbarma, General Manager, Gas Authority of India Limited, to present his speech. Please, sir.
It's in fact really a very great opportunity for me, and that I could connect with such a high-level intellectual personnel who are on the board and connected through the virtual. It has become possible only because of the chairman, the NC Devnath Sahab. He used to visit our office and elaborate us regarding the activities that Institute of Engineers State, Tripura State Chapter activities, and we are really applaud because of his deed, in spite of less in numbers because of the size in state, although the center could stand third ranking. That is a really, again, one thing I must congratulate on the 32nd birth anniversary of this institute center, and I really thankful for that. And I must also congratulate the dignitaries and faculties who are presenting actually regarding the advancement in production engineering. As far as myself is concerned, I would like to draw to the student that this is the only department who can facilitate the product processes and the end users product quality, how it can be made in a better way, in a cost optimized, lesser times and lesser time, energy, manpower, and lesser resources. So without this department, none of the industries could think forward. And this is the prime mover for any industries. And in order to increase their efficiency, rather we can say reducing the inefficiency and converting into efficiency. So I must congratulate and thanks to the state chapter for selecting the topics that will at least clarify the upcoming student who are present this out here. And if you are through with this thing, basically it will be analyzing the operation and design workflows, processes, and so that it will try to meet the product standard quality. So that means closed loop cycle actually. So we must look forward what are the advancement through this thing expertise. Like Dr. John, he will be presenting regarding the welding procedures. As far as my organization is concerned, we are basically having a cross-country pipeline of around 15,000 plus kilometers. So these welding procedures are prime mover for my organization is concerned. So certainly the development or advancement in welding procedures will be our topmost priorities to adopt the changes so that our things will move intact and it will be more this thing in a perfect way. So I'll be certainly looking forward. And as one more thing, I would like to connect with the student out here, all the institution. I can at least request the faculty members, they can bring their student for industry visit, not in a more in numbers, in a less, like 15 numbers in each group. If it is a 50 numbers, they can make it three groups so that we will be able to show what industry is actually doing and what are the requirements in the industry, so that the student could take their preparation accordingly in line with that if they want to go for any PSUs like my organization, and so that they can prepare themselves that if you satisfied, if you desiring, you can certainly apply accordingly and prepare in line with that. So this is the facilities where I have in my Tripura state, we have around 60.4 kilometers of pipeline. So we will be adding now another 5 kilometers. So 65 kilometers of pipeline we will be having. And we are supplying gas on an average around 1.5 MMSCMD of gas. And this gas are being mostly utilized for power plant, as well as then CGD and CNG and PNG. Basically, CNG and PNG is being looked after by our Amberson Shop. It is a joint venture of GAIL, TIDC, and Assam Gas Company. So we are bulk supplier basically. My organization is a bulk supplier, 50,000 and above. Gas will be directly supplied through GAIL, and if it is less than 50,000, it will be looked after by TNGCL in and around Agartala city. So, and I must also apprise our chairman sir. Please do come forward to my organization, because there are many engineers. I think they are yet to be take membership for this Institute of Engineers. So that I will at least commit you. I will try to facilitate all those things so that more number of engineers should be enrolled within this Tripura chapter. So with this, and again as the honorary secretary sir also. So that is my commitment. And the young student, I will certainly love to see you all, and will certainly guide you all. Very recently, this ICFI student management, the management courses student, we offer them to visit our organization, our establishment. They would like to understand what actually GAIL is doing here. It may be in terms of business of this thing, business procedures, or human resource, finance, and contractual procedures and all. So we are directly apprising them for each and every departmental like that way, so that they can feel what actually industries are desiring and what they are doing. You'll be having some at least basic idea. And we very recently we also tie up with this thing. There is one skill development institution. They are basically secretary level students. The course are offering. They are offering for secretary level, office secretary like that. So on job training purpose, we had around MOU type with them. They will be bringing around 10 students for us for 3 months training. On job training will be there. We'll be offering them this. So if the opportunity is here, so we all must encourage for that opportunity, whatever. I think my brother John, we are happen to be from the same college. I also passed out from Neris. So for industrial tour purpose, our faculties, they used to take us, this Namru, Digboy and all, HFCL and all, for just have a feel about the industries. So those are the days I also started, I would like to convey my beginning of my career. I started my career with the teaching only in the NIT. Currently, right now it is NIT Agartala. Earlier it was Tripura Engineering College in the year 1996. I worked there as an associate the lecturer in mechanical department for 1 year. Thereafter only I switched over to this organization in Delhi. I joined in Delhi. So now I have returned back here. So it will be my privilege to receive any faculties to come with a plot to our organization, so that we can facilitate them what exactly mechanical department. For the mechanical department, we have the welding of pipelines, various material, dissimilar materials as well as similar materials. So those are the things you can certainly see. Even one pipeline project is still running on. So wherever you came, you can see the HDD also, horizontal directional drilling, how the road crossings and all without cutting, open cut, without disturbing the main line, how pipelines are being pulled out and throw this thing and normalize. So those are the things you can come and see for mechanical department is concerned. You will have a feel how the cross-country pipelines are being installed across the globe. It is almost the same. So with this word, I must again thank you very much for Chairman Sahab. giving me opportunity to have at least to speak something in amongst the student and faculties and with such a senior dignitaries. Thank you very much.
Thank you so much, sir, and we'll definitely look forward to your suggestions. Now, I would like to request the chief guest of this program, Engineer A. Anbarasan, sir, Managing Director, Tripura Natural Gas Company Limited, Agartala, to give his presentation.
Good afternoon to all of you. Respected Devnath ji, respected Sibaji Bhattacharya ji, and my dear professors from through web conference. It's indeed very pleasure for me to be here to attend this program, 32nd. Programs on Institute of Engineers, this one. Rather, it is normally there is a gap between two departments. One is production engineering and mechanical engineering, because the difference is mechanical engineering, they study heat and mass transfer, whereas production it is left, I think. Now, I think very recently it is, they are not still, it is difference is there, I think. Because of that, the production engineering students used to lag employability little bit tough, in the sense in energy sectors they are being deprived. They have to qualify through GATE and everything through mechanical subject only, even though they are specialized in production engineering. So the students, if they specialize or on their voluntarily they study heat and mass transfer, I think that will be easy for the employability in the after completion of the course and everything. So the other technology, other experts, this advances and everything, that is total quality management, work study, time study, enterprise resource planning, all those things, definitely production engineers, they are expert in this one. Apart from that, energy sector also, if they want to have this one, this is a need of the hour in the India, all over the world, is the energy corridor, like your power grid, gas grid and everything. Like you can say in southern India, the renewable energy is more. Around in Tamil Nadu, around 9,500 megawatt is being produced in wind energy. Sometimes it becomes surplus. We were forced to stop the power, renewable energy power plants. When I was looking after the 100 megawatt power plant, we were forced to stop the power plant, that is renewable energy windmills, because there is no transmission, there is no taker, because there is no proper grid arrangement to transmit to other states and everything. Like that, in Tripura, we have surplus power from gas. Rather than wasting the gas to power plant, we can use the renewable energy. We can, lot of wind is available for wind electric generation. 10 km/h wind speed is more than enough. So sometimes we get even more than that also. So only the issue is the challenge is transportation of heavy equipments to the terrain. This tough terrain to the northeast is a very big issue. If some the challenges are overcome, we can, I think government can, and our engineers, we can think of putting this renewable energy like in the as well as solar plus wind energy, and also so that the natural resources like the thermal gas, coal availability, those things can be utilized in the other sectors like in domestic gas or other sectors and everything. Already the government policy is that priority sector is deep domestic as well as CNG sector, whereas the power plant and everything, they are not in the priority sector. So since the shortage is there, so in due course they may be deprived of giving less allocation to the power plant and everything. So this is a challenge for engineers like us. So youngsters will think of making the corridor wherever the surplus energy is there, that can be transported through transmission through lines and everything. So those things can be thought of this one. So after theoretical and everything, once you come out, the employability skill has to be developed. Because the person who is theoretically very sound in students getting 98% and above, but they are not able to qualify through GATE and everything. So once they are not qualified, they are not getting employment. So that gives frustration and everything. They are not getting good jobs and everything. So that employability skill also needs to be developed during the course itself. So that for that, I think they can go for industrial training and everything. Like Biswajit told, GAIL is there, ONGC is there, TNGC is there. So wherever employability skill they can develop also, that will improve them apart from this theoretical knowledge. This, especially this ERP, enterprise resource planning, that is the talk of the day because of automation and everything. That is helpful to the production, not only to the production people, any engineering graduates. That is more important also. In TNGC also we are using enterprise resource planning and everything. We have around 28 CNG stations. That is spread all over 4 districts of the Tripura. And we to cater these around 60 tons to 70 tons per day we are supplying to the CNG station. So this we are supplying through that 42 LCVs supplied by Tata vehicles. So this being coordinated through GPS coordination and everything. So this logistic control, all those things are through the ERP and everything, and it is being monitored through mobile application system itself. So such planning improves as the logistic control so that the customers are not hampered, they are getting satisfied and supplied everything. So like that, we have enterprise resource planning, and in the inventory control also, in the service sector also we are doing these things. So uninterrupted gas supply is ensured through pipeline and everything. And for monitoring also these things, we are using it through SCADA system also we are going to commission very soon. So such things will, automation will improve definitely the quality of the life, and manual intervention will be, we have almost employed around 500 people in this TNGC sector, retail marketing. So in spite of automation and everything, we require this much people. So automation further improvement will in the system will definitely improve the quality of the life and system improvement everything. So I request the students, youngsters who will be further improvement in the system and everything. So you can come forward. This type of forum will definitely will help us to enhance the knowledge as well as to go for R&D, all those things, everything. I take this opportunity, and once again I thank you, Devnaji and Bhattacharya and others for giving me opportunity. Thank you very much.
Thank you, sir. Thank you so much. Now, I would like to request Dr. Saurabh Datta, Associate Professor, Department of Mechanical Engineering, NIT Rourkela, to present his paper on the topic Engineering Applications of Auxetic Metamaterial Cellular Structures, Fabrication through Additive Manufacturing.
Okay. Thank you, madam. Madam, am I audible?
Yes, sir.
Hello. Okay.
Yes,
Okay.
sir.
Okay. Can you see my screen?
No, sir. Not
Okay,
yet.
just.
Yes, visible now.
It is visible, no?
Yes, sir, it's visible now.
Okay, 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 okay. So we are in the title page, right?
Yes, sir. We are having the title page.
Okay, okay. So good afternoon. First of all, I would like to convey my heartfelt thanks to the organizers, I mean Institution of Engineers India, Tripura State Center, for inviting me for this one-day seminar on advances on production engineering. I am indeed happy to be a part of this program. So directly, I'm going to my topic, that is engineering applications of oxidic metamaterial structures, fabrication through additive manufacturing. Now, first of all, what is additive manufacturing? It is basically layer upon layer deposition to realize a final part. So it differs from conventional subtractive manufacturing. For example, turning, there we see excess material is being removed in the form of chip. So layer-wise subtraction. But here in additive manufacturing, layer upon layer deposition to realize a final part, 3D part product. Initially, this technology came into existence in the name of rapid prototyping, in which basically its objective was to rapidly produce prototype, not direct functional part product. So that is why it is named as, initially it was named as rapid prototyping, but nowadays direct products can be possible to fabricate through this route. So these terms are brought under a common umbrella, and which is termed for 3D printing, where our objective is to produce prototype. This is called rapid prototyping. Where our objective is to produce direct tool, it is called rapid tooling. Or when our objective is to produce some functional part. So all comes under same umbrella, that is called additive manufacturing. Now, frequently used terms are additive manufacturing, additive layer manufacturing, additive digital manufacturing, layer-based manufacturing, layer-oriented manufacturing, rapid technology, rapid prototyping, rapid tooling, digital fabrication, 3D printing, 3D modeling, all are synonymous. All come under the common term, that is additive manufacturing. Okay, it is said that additive manufacturing is one of the enablers of industry 3.0 and 4.0. So that is industrial revolution 3rd and 4th. You know, in first industrial revolution, we experienced the essence of mass production. In second industrial revolution, we have seen experience power driven, utilization, consumption of power, steam power, hydraulic power in case of production. In third industrial revolution, computer, utilization of computer and automated machine tools. And fourth industrial revolution is combination of computer, information technology, digitization of the process system. Okay, and in fourth industrial revolution, a new concept has come or will come in the upcoming days, that is called smart factory. That means a factory can run without involving human participation. We can imagine some product design is developed somewhere else in the globe, and the product is to be manufactured at some other places, and the process is to be controlled by some other country. So interconnected chain. So the concept of smart factory without involving any human or operator. So in upcoming days, we are going revolution 4.0, and additive manufacturing is the enabler of this. Now, additive manufacturing is a layer-based automated fabrication process for making scaled three-dimensional physical objects directly from 3D CAD data without using part-dependent tools. In conventional manufacturing process, say for machining process, we require tool, but additive manufacturing can develop, fabricate a product without involving any part-dependent tool. Turning tool, milling tool, boring tool. But in additive manufacturing, no tool. We have to model the design in a software, then slice the model into n number of cross sections, and accordingly that layer wise material is to be deposited one upon another or layer wise stacking fashion to realize the final part. So it was originally called 3D printing. So additive manufacturing refers to technologies that create objects sequential layering. This figure represents the left-hand side CAD image of a teacup, and the right side two images are there. You can realize it is fabricated by depositing layer upon layer, but in the right two images you can see there is difference in layer thickness. So from this we can understand layer thickness is a parameter to influence roughness finish of the part product. Okay, so layer upon layer deposition. Now let us articulate what is the difference between additive manufacturing and subtractive manufacturing. Figure A, you see a material block is there. So through subtractive manufacturing, unwanted material layers are removed and we realize a 3D object. But you see the volume of waste is very high. But B, figure B represents additive manufacturing where the feedstock material is metallic powder. For example, metallic powder, and this powder is consolidated layer-wise layer to realize the final product, and see the waste is nil or negligible. Okay, so that means as compared to subtractive manufacturing, additive manufacturing is economic, environment friendly because waste is minimal and it adheres to green and sustainable manufacturing philosophy. So that is why industries are being encouraged to adopt additive manufacturing technology rather than conventional subtractive routes or conventional production routes. Now let us understand the basic differences. In additive manufacturing, layer upon layer deposition to develop desired solid 3D product. Whereas in subtractive manufacturing, layer by layer material is gradually removed, subtracted from a solid block to fabricate 3D product. In additive manufacturing, the concept is usually suitable for materials having low melting point, such as plastic. Nowadays, metal additive manufacturing have come into picture. But in subtractive manufacturing, large range of material, variety of material we can fabricate. In additive manufacturing, volumetric density, thus weight of the constructive material of final component can be controlled during operation. The volumetric density can be controlled. For example, a powder bed is to be fused or melted. One bed is formed, then another bed of powder is consolidated and it adheres to the previously developed layer so as to realize a final product. Then the volumetric density we can control. You know, if energy input, heat input is more, there will be more melting and more consolidation. So less of porosity, void formation will be less. So by adjusting process parameters, we can control volumetric density of the additively manufactured product. But in subtractive manufacturing, For example, machining, we cannot alter density of the raw material. Okay, material density cannot be controlled during operation. Density of object remains same than with that of the initial solid block, usually a cast product. In additive manufacturing, no material waste takes place in these processes. But in subtractive manufacturing associated with material waste in the form of chips, scraps, dissolved ions, vapors, etc. In additive manufacturing, complex shapes can easily be fabricated. Okay, so that is the added advantage. Complex shape, intricate geometry, profile, control, that which is impossible to fabricate through subtractive manufacturing, we can easily fabricate through additive manufacturing. That is what I shall going to discuss, that is auxetic metamaterial. Now, subtractive manufacturing process have limited capability in fabricating complex shapes. Structures containing fully closed internal hollow parts can be produced by these processes. Fully closed internal hollow part, but this we cannot fabricate through subtractive machining. Then additive manufacturing processes are applicable to a narrow range of material. Variety is less. This is the disadvantage of additive manufacturing. Okay, different manufacturers are there they offer additive manufacturing setup, and each setup is suitable to handle a variety, less number of material types. But in subtractive manufacturing, material variety is wide. In additive manufacturing, these processes are time consuming. You can imagine layer upon layer deposition. Okay, so it is time consuming and to some extent costly, but can provide superior quality and desired property with or without requiring any further processing. Okay, why it is costly? We shall see some additive manufacturing process utilizes laser beam, electron beam, and etc. Whereas in subtractive manufacturing, these processes are time efficient and economic. These are usually suitable for mass production, where requirement of product quality is not so tight. Now, advantages of additive manufacturing in brief: complex geometries. Complex geometries which is difficult or impossible to fabricate through conventional routes can easily be fabricated through additive manufacturing. Next is little material wastage. So that is why it adheres to green and sustainable manufacturing. Okay, and it is called environment friendly. Then rapid prototyping. Design alterations can be completed quickly and efficiently because of the digital process. Improved strength and durability. Parts that were previously assembled from multiple pieces are fabricated into a single object. Previously, in conventional route, different parts are to be fabricated and these are to be assembled. But in additive manufacturing, it eliminates the step of assembling. The entire product can easily be fabricated. Then unique objects and replacement pieces. Additive manufacturing is able to create unique objects and replacement segments where the original pieces are no longer produced. Suppose an integrated component is there, some part is to be replaced. So no need to produce the entire component, only the replacement part is to be fabricated and it is to be replaced by the broken part. This is the added capability, added advantage. Then easy to change or revise the product. Additive manufacturing enables designers to produce multiple versions of a single design in a cost-effective manner. Because before fabrication, the part is 3D model generation through software. Okay, during these phases, by means of some simulation and optimization, optimized geometry and design are to be exercised before going to final fabrication. So these are the unique capabilities of additive manufacturing. Now, additive manufacturing is classified mainly in two categories. One is metal-based, one is polymer-based. Now, metal-based additive manufacturing, broad categories are binder jetting, powder bed fusion, sheet lamination, direct energy deposition. Okay, so this classification is mainly based on the type of the heat source is utilized to melt or fuse the feedstock material, and number two, the type of the feedstock material. In some cases, you will find powder bed is selectively fused or melted by means of high intensity laser beam or electron beam. One cross section is produced, then you lower the build platform, then again recoat another powder bed, and next cross section you fuse. So this cross section, fused cross section, will adhere to the previously built cross section. So layer wise layer deposition, you continue the process until the required build height is achieved. So this is called powder bed fusion. Direct metal laser sintering, selective laser sintering, selective laser melting, electron beam melting, this comes under this category. Okay, here feedstock material is powder. In some cases, feedstock material is metallic wire. So example is wire arc additive manufacturing. So you can imagine over a substrate plate, one bead-on plate welding is developed, upon which another bead, then next bead along Z direction, vertical direction. So this is called additive manufacturing. If you deposit bead parallelly over the substrate plate, this will be called cladding. Okay, so deposition of bead layer upon layer along vertical direction. So this is applied in wire arc additive manufacturing. So since time is short, I am not going into details of these processes, just this polymer additive manufacturing, the basic classifications are VAT photopolymerization, material extrusion. It is nothing but fuse deposition modeling that I shall be discussing. Then material jetting, then powder bed fusion. It is common to both polymer-based additive manufacturing and metal-based additive manufacturing. Process principle is same. Now applications. So 3D printing does not require any mold as a precursor to manufacture. This product is produced through additive manufacturing. No mold is required. So this is the advantage. In additive manufacturing, multiple parts of varied geometry or design can be produced in one cycle. Okay, next, the size is no bar. Small to medium, medium to large size components can be produced through additive manufacturing. Next is geometric complexity is not a limitation in additive manufacturing, 3D printing. We can't imagine to manufacture this type of structure through conventional manufacturing route, but this can be fabricated through additive manufacturing. Now, additive manufacturing can be used to produce patterns for casting. Then molds for casting we can create. Direct tooling for additive manufacturing can be used to produce direct tool. Then 3D printing can make parts in biocompatible materials. Okay. Then prosthetics, implants, and of course, mass customized implants, prosthetics can be fabricated through additive manufacturing. Okay. And the material you can consider titanium alloy, Ti6L4V. So in biomedical, additive manufacturing has huge application. Then other medical applications are there. Then aerospace application. If you go through literature, you will find any metal-based additive manufacturing is associated with fabrication of aerospace component of titanium-based alloy, nickel-based superalloys, for example, Inconel. Because additive manufacturing is has become very popular to produce aerospace structural components because it substantially lowers buy-to-fly ratio. So that is why it is used in aerospace component. So what is buy-to-fly ratio? I shall discuss in next slide. Then automotive component, structural parts of automotive industries. Then jewelry. Then comes medical applications. Some of this I have already discussed. Then sports industry. Then furniture. Then textiles. Then toys. Then comes tool mold making. Then additive manufacturing. It is said that additive manufacturing has brought revolution in our kitchen. Okay, so in food processing industry also, this technology can be applied. So layer upon layer deposition of food, substances. Now, buy-to-fly ratio. The family of additive manufacturing processes is particularly attractive for material efficient production of items that would otherwise have a buy-to-fly ratio. The buy-to-fly ratio is simply the ratio of the mass of the starting billet of material to mass of the final finished product. Let's see the picture. The left hand side starting billet and the right hand side the final product. So buy-to-fly ratio is mass of the starting billet to the ratio divided by mass of the final part. Now in conventional machining process, there is huge. So in conventional machining route, buy-to-fly ratio is excessively high. But in additive manufacturing, since there is no material deposition, buy-to-fly ratio reduces substantially. That is why aerospace industries are being encouraged to use additively manufactured aerospace components. So that is why if you go through any literature on metal-based additive manufacturing, you will find this is of Inconel, titanium alloy, aluminium alloy, etc. Because these are huge application is in aerospace engineering. Another in continuation with buy-to-fly ratio, the left hand side you see the stiffened panel is fabricated. Stiffened panel means the plate or sheet which is called skin and upon which these are called stiffeners. Stiffeners are attached because aircraft body is not a solid material. It is fabricated through stiffened panel to reduce mass or weight, but without compromising stiffness. Now you imagine if you want to produce this stiffened panel through conventional machining route, so what we'll have to do? We have to remove these square blocks from the sheet. But in additive manufacturing, this stiffened panel can easily be fabricated with associated with low buy-to-fly ratio. So this is the advantage of additive manufacturing. Waste is minimal. Now, disadvantages of additive manufacturing. questionable accuracy. Suppose you are producing a component by layer upon layer fusion or melting of powder bed. Since it is powder and depending on the process parameters, for example, laser beam power, then laser scanning speed, etc., there may be chance of porosity, void, crack. At the same time, you can imagine one layer is deposited upon which another layer is deposited. So thermal effect of presently layer the layer which is being fabricated, it affects the previously deposited layer. So there is complicated thermal history. And of course, in manufacturing, in general, heat is the enemy. So that is why questionable accuracy. At the same time, since layers are deposited along Z direction, vertical direction, in metal-based additive manufacturing, you will see the microstructure as well as mechanical property is not homogeneous. Anisotropic mechanical property, it varies along Z direction. So this is the disadvantage. And to overcome this, what we have to do after fabrication, the product is to be post-processed. Okay, heat treatment to to make the microstructure and property isotropic in nature. Next disadvantage is support material removal. You are going to deposit layer upon layer material. Okay, so first layer where you will deposit over a support plate and on a support plate. Upon first bit, second layer, then third layer. So when the final part is produced, you have to discard the support material. Then limitations of raw material. I have already discussed different machine suppliers are providing different machine based on different additive manufacturing technology, and a particular machine is capable of dealing with a limited type of material. So limitation of raw material is there. Then considerable effort required for application design and for setting process parameters, because at the initiation, first you have to develop the 3D CAD model, then you have to apply some algorithm for efficient slicing of 3D model into n number of cross-sectional layers, so as to ensure layer-wise layer deposition. Next is material cost. You see, powders are very costly as compared to metallic ware. Then material properties, I have discussed, due to complicated thermal history, you will find anisotropic material property within the build part. So to overcome this, we have to go for post-processing operation, say for heat treatment, hot isostatic pressing. Okay, and since it is the surface finish is not good, dimensional accuracy is not good, we have to go for post-machining operation. And intellectual property issues, because different manufacturer has proprietary for that particular setup. So it is not, widely open. The technology is not widely open. Limitations of size. Okay, you see in electron beam melting, additive manufacturing, the electron beam can interact with powder particle in a vacuum. So your size of the part to be fabricated is limited by the size of the build envelope, build chamber. But whereas in where are additive manufacturing, okay, open atmosphere, you can fabricate the component. So there is freedom fabrication. So it differs from technique to technique. So based on that, additive manufacturings are categorized into various techniques. Then cost of printers are sometimes high depending on the technology. If it is electron beam based, it is more expensive than where our additive manufacturing setup like that. Then unchecked production of dangerous items. In additive manufacturing, if we are unable, if we are capable of producing the 3D part product in a model in 3D software, we can easily develop a product. So people may develop their intended weapons and dangerous items. So this is disadvantage. So government should impose restrictions to check this the dangerous tendency. So still it gives, advantage as compared to conventional machining. Okay, so it is said that in upcoming days, conventional manufacturing routes will be obsolete. Every component is to be produced through additive manufacturing. So generic additive manufacturing processes are, let me go through, time is short. You have to develop a CAD model, then model is to be developed in STL file format. File is to be transferred to the machine. Machine can read the file. Then machining parameters are to be set. Then fabrication, layer-wise fabrication is to be accomplished. Then you have to remove the product from the built envelope. Then support removal, post-processing, heat treatment, post-machining, then application. These are the generic steps. Now, how different additive manufacturing strategies or technologies are being classified? So I have discussed, it is based on technique used for creating layers. Sometimes you have to fuse powder bed. Sometimes you have to deposit molten material by melting feedstock wire. Then techniques for bonding on or consolidating layers together, then speed, then layer thickness, range of material, accuracy, cost. So depending on that, different additive manufacturing technologies. So these are the possible materials presently being exercised for additive manufacturing. Next come unique capabilities of additive manufacturing, functionally graded material. What is that? This material is nothing but one or more properties. It may be composition, it may be mechanical property, and it can vary along a particular or multiple directions. For example, human bone. Okay, natural example of functionally graded material. What is that? Outer surface, outer part of the bone is stiff, but if you go interior core, it becomes softer. Okay, so it is called functionally graded material. It may be composition. Suppose along a particular direction, composition is varying, or microstructure is varying, or mechanical property is varying, either at least one direction or multiple direction. So that is called functionally graded material. You can never fabricate this type of component using conventional processing route, but additive manufacturing has the unique capability to produce. The right hand side top picture, I have shown cross section of a dinosaur bone. You can see the outer portion, the pores are very small in dimension, but inner portion pores are large. So pore gradation along this the direction mentioned. Okay, so this you can manufacture through additive manufacturing. Then comes, I will not take much time. The main focus of my topic is auxetic metamaterial, and additive manufacturing is capable of producing that particular material. What is metamaterial? For example, honeycomb, then feather of a bird. So these are examples of metamaterial. So by definition, metamaterial is basically a structure which has a constituent unit cell and which is repeated throughout the structure. For example, honeycomb, one hexagonal unit cell and it is repeated. So this is called metamaterial. Okay, now out of these metamaterials, some metamaterials are there depending on the unit cell structure. They exhibits negative Poisson ratio. So these metamaterials are called auxetic metamaterials. So all auxetic materials are metamaterials, but all metamaterials are not auxetic. Only those metamaterials which correspond to negative Poisson ratio are called auxetic metamaterials. What is negative Poisson ratio? Suppose a slender body is subjected to a tensile load. So what will happen? Its cross section will reduce and it will elongate. But in auxetic metamaterial, upon application of tensile strength, it will elongate along axial direction, but cross section will enlarge instead of reducing. If we apply compressive strength, compressive force, what will happen? In conventional material, cross section will tend to increase, but in auxetic metamaterial, upon application of compressive force, the cross section will reduce. So that is why they correspond to negative Poisson ratio. And this property, due to this property, these materials have tremendous, huge engineering application. Along with negative Poisson ratio, they impart improved fracture toughness, improved energy absorption capacity, high indentation resistance. So this figure, so A, the left hand side figure, conventional material, you see it is pulled, cross section reduces, but auxetic material, upon pulling, cross section increases. Okay, so next is high indentation resistance as compared to C. A is non-auxetic material, that is metamaterial, honeycomb. I have cited the example of honeycomb. It is not auxetic, but the next structure is auxetic. You see, improved, better indentation resistance. So applications of auxetic structures, sports application, you see, auxetic implant. Okay, within the implant, some auxetic structure is to be there. Soft robotics, auxetic garments, safety jacket. Okay, then auxetic sandwich panel for building construction. Due to such structure, they can impart better seismic protection. Okay, seismic shock absorptivity. So in military application, shock absorber, auxetic composite panel, ballistic impact absorber, defense application. Okay, so various applications are there. But the thing is, how to fabricate this auxetic structure? The left hand side top picture, undeformed auxetic structure. Upon compressive loading, you see the cross section tends to increase. Okay, now auxetic structures, 2D structures, 3D structures. The right hand side top structure, you see 3 structures are there. First one is trichiral. So the round portion is called node, and nodes are attached with ligaments. Okay, so this is node, 3 ligaments are there, trichiral. Second, picture number B is tetrachiral, and picture number C is hexachiral. So auxetic metamaterial architecture is defined by unit cell geometry. The bottom left picture, you say unit cell red in color, and the topological parameters, cell geometrical parameters are ligament and node, length of ligament, node diameter, height of the ligament, height of the node. By varying these parameters, you can modulate or tune the extent of auxicity. That means to what extent the negative Poisson ratio will be depending on the application. So by numerical simulation, it is easy to design and simulate its performance. But how to manufacture? The right hand side bottom picture, 3D auxetic cellular structure. Okay. So no conventional manufacturing route is there to fabricate such structure. But in additive manufacturing, if it is based on polymer, fuse deposition modeling, if it is based on metal, powder bed fusion, or laser powder bed based additive manufacturing, you can utilize to fabricate such structure, to realize such structure. First, you have to develop the CAD model of the structure. Then you divide the structure into multiple numbers of layers and cross sections. You deposit feedstock material layer upon layer according to the individual cross section design, and realize the final part is realized. So this is the unique capability of additive manufacturing to produce auxetic metamaterial structure for diversified engineering applications. So this is some aspects of fuse deposition modeling. Since time is less, I'm not going into that. In fuse deposition modeling, it is based on polymer, but nowadays metal fuse deposition modelings have come into existence. In fuse deposition modeling, you see the
Doctor, please.
yes.
Can you just show your presentation to help? We have another presentation also.
Okay, sure.
So that, the
Okay.
participants can interact with you in the question hour.
Okay. So let me wind up. So fuse deposition modeling, I am not going into detail. I am going to just show one picture. The left hand side is SolidWorks model, and the right hand side is fabricated tetrachiral auxetic structure that is developed by my student, and it is based on fuse deposition modeling, and the material is ABS plastic. And we have conceptualized the 3D unit cell of the tetrachiral auxetic structure, and we are shortly going to fabricate this. Oh, okay. Sir.
Thank you, sir.
Thank you for your patience.
No, sir, it was a beautiful presentation. I'm sure our students and of course we will also be benefited from that. Thank you, sir. Now, I would like to request Dr. John Debbarma, Associate Professor, Department of Mechanical Engineering, NIT Agartala, to presentation on his topic. Now, before that, I would like to request Engineer Chinmoy Devnath, sir, Chairman IEI Tripura State Center, to welcome sir with a memento. Thank you. Now, Dr. John Debbarma will present his presentation on the topic friction stir welding of thermoplastics using a noble self-heated tool.
Hello. I thank the organizer for inviting me to deliver a lecture on the one-day seminar of production engineering division on advances in production engineering. So my presentation is basically on a research-oriented paper. It's a development of a self-heater friction stir welding tool, which is required for welding of thermoplastics. Now, if we talk about the engineering materials, why actually we have chosen thermoplastics for that? Now we know that there are different kind of engineering materials. Ferrous material is a kind of engineering materials. We have got non-ferrous materials also. We have got ceramic materials, composite materials, and plastics. So if we talk about plastics, it has been derived from the word plastikos, is a Greek word. Plastic means it can be able, it is able to be shaped. It also can be molded. So there are two different kind of plastics basically. I'm not going into more details. All of us, we know thermoplastics and thermosets. Now, we have chosen thermoplastics as a material because of its wide applications and its unique properties. Because thermoplastics are well known for its high strength, toughness, it has got a good hardness, it is also chemically resistant, it is durable, and thermoplastics like nylon has got a self-lubrication property, transparency, and waterproofing, etc. Now, there are different examples of thermoplastic materials such as ABS. ABS is not only thermoplastic, it is also an engineering plastic. Engineering plastics are, they can withstand high load, and it is also resistive to the weather conditions. PEEK, PEEK, as you can see, this is also a kind of engineering plastic. So ABS, polycarbonate, polyethylene, these are the common common thermoplastic materials. The Kevlar, polyamides, vinyls, fluorocarbons. So these are some of the examples of thermoplastic materials.
Slides are not visible.
Is it visible?
No, slide is not changing. The first slide only is there on the screen.
Maybe, okay, just let me check.
Yeah, okay. Okay.
Okay, I think if we are going for full screen, there is some problem. So is it visible now? Is it okay?
Yes, sir. Yes, sir.
Okay, thank you. So if we talk about the applications, certainly the thermoplastics are used in dashboard, car frame. It is also the mobile we have got in our hand, the phone covers. These are also made of thermoplastics. Different electrical products, gears, plastic gears, glass frame, cables, even windows. These are made of thermoplastics materials. For example, that polycarbonate is a material which are used in windows. Now, certainly, there is a necessity for joining, because if we talk about any ideal design, no joint is having no joint, it is never possible. So any design, if we go, certainly joining is required. So there is always a necessity, and in order to produce, integrate composite parts, the components have to be joined together by using various techniques. Certainly, we can go for mechanical fastening, which is one of the joining technique. We can go for adhesive joining. We can go for thermal joining, like using laser, hot gas, etc. And we can also go for friction joining, like spin, linear, ultrasonic, friction steel, which I'm going to discuss today. And there is also electromagnetic joining by using resistance, induction, and microwave. Now, it has been seen that from the researches done so far, friction stir welding is capable of producing, of course, it is this data, whatever you can see here, up to 95% joint efficiency can be obtained with the help of FSW. So that's why this is one of the reasons why you have chosen friction stir welding as a process for joining of thermoplastic. Now, through the review from literatures, if we talk about the existing process, we have got hot to weld welding, but there is a problem, it needs long cycle time. Similarly, the other processes like laser welding, ultrasonic welding, vibration welding, all these are having some disadvantages. So that's why there came the development of the research of thermoplastics by using FSW, which started in the year 1997. And it has been seen that successfully the people could join different thermoplastics materials like polypropylene, polyethylene, PVC, polycarbonate, ABS, etc. Now, one of the major advantages, it's a solid state procedure. And that means whenever welding takes place, the welding takes place in solid state manner. It helps to preserve the material's mechanical properties. But however, FSW of polymeric material, if we say, of course, for metals, it is a solid state material fully, solid state procedure fully. But in case of polymeric material, the FSW of polymers is not absolutely a solid state process. Rather, of course, the material, a little bit of material melting, softening also takes place during the process. And of course, there are different molecular weights in chain length in polymers, which are equally important behind the quality of joining. Now, welding in this process, they use friction as the major resource. The weld is created by the frictional heating, mechanical deformation, and here, unlike other welding processes such as submerged arc welding or arc welding process, the filler material is not involved. So without the use of any kind of filler material, simply the action of friction only by generating heat can be joined. So as you can see here, this is a schematic drawing of the friction stir welding. And for that, we also require a tool which is responsible for developing the heat with the help of friction. Whenever the tool is rotated and the friction in between the shoulder and the workpiece will create heat, it will, due to the rise in temperature will cause the material to soften, and it will get soften and some melting will take place, of course, as I've already mentioned, but ultimately due to the solid state, in the solid state phase only, the material mixing takes place, and this is how the bonding is taking place. Now, one of the, if we talk about the advantages, it's a solid state process, solid phase process. The distortion is less, good dimensional stability and repeatability, excellent mechanical properties in the joint area. It can replace multiple parts which are joined by fasteners. No sealing gas is required in this process. Minimal surface cleaning is required, eliminate grinding waste, and no harmful emissions, so forth. Now, if we look at the microstructural regions in the transverse cross-section of a friction stir welded joint, there are 4 different microstructural zones. One is the unaffected material. You can see A and A is the unaffected material or the parent material. Then B is the heat affected zone, HEZ. C is the thermomechanical affected zone, PMEZ, and D is the weld nugget. Now, as we have said, the shape of the welding tool also plays an important role in the quality of welding, especially the shape of the stir pin. It has been seen that for polypropylene, cylindrical, square, and triangular headed threaded tools are they have been successful. For ABS and polyethylene, cylindrical geometry, conical geometry, and whenever we use threaded pin profile, then less tool force is required, and with the help of triangular, square, or group with square pin profile, defect-free welding could be achieved. Now, direction of thread and rotation also plays an important role. So the left threaded pin profile with counterclockwise direction rotation creates a good welded region, of course, with good properties of weld. So as you can see in this figure, that setting of the tool and its clockwise direction to, and also the parent material, And in the B, you can see the effect of the tool rotation in clockwise direction. Okay. So what happens, the tool throw the material to outside through the thread that is present on the pin. So this shows the contribution rate versus the different welding parameters. You can see here that the tool rotation has got the most significant influence. So almost 73.85% on the contribution of welding. Then comes the contribution of tool traverse speed and then tilt angle, because the pin also is set at an angle when the welding is being done. Now, these are, since there is a shortage of time, I'll just move. But here we are just showing that how the different people have used different kind of tool for tool pin profile for welding the thermoplastic materials. So here, as you can see, that this is a welding tool and stationary shoulder assembly, and figure 9 shows the different threaded pin profile. Now, this shows a novel FSW tool because my topic is on development of a novel tool for friction stir welding of thermoplastic. So different people also have worked on different tools. This is one of the tools which has been developed by Esam, and by using friction also only, he has developed a kind of tool. This is another, the next one is a tool which is using the heating element inside. So this tool was, by using this tool, better weld surface finish and chip formation during welding could be, brought down. Material loss also could be minimized. And it has been seen that whenever we are using some external heat source, the tensile properties of the friction stir welded joints have improved. So, this is another tool which uses hot air inlet. Now, this is another tool which uses induction heating for friction stir welding. So, as an inference, we can say that whenever we talk about polymers are low frictional coefficient and thermal conductive materials. So, unlike metals, it is quite difficult to separate the frictional tool heat to the workpiece. Because if we talk about welding of metals, certainly the frictional heat can be developed very easily. But in terms of polymer, so since it has got low thermal conductivity in comparison to metals, so it is very, very difficult to supply the frictional heat to the workpiece. That's why there comes the need of giving some external heat source. And the effect of process parameters on heat generation, it was seen, and it has been seen that a typical set of process parameters needed to obtain a sound welding. So hybrid welding also can be done in order to get a better joining. And if we talk about polymers, these are soft in comparison to the materials. That's why higher levels of flange depth cause deterioration of the polymeric material. So, for example, in metals, we can go for, whenever we particularly talk about friction stir welding of metals, we can go for higher level of flange depth because that ensures the forging of the materials, and which also involves better mixing of the materials. But in case of polymeric material, this is not possible because polymeric materials are soft. So that is the problem. So that's why the idea of developing the tool came up in our mind. So this is the machine which is present at NIT Agartala, where we have performed the experiments. And this is a 3-ton friction stir welding setup. Now, we have used a different kind of tools. First one attempt, step by wise, we have done the experiments. First, the attempt was to join a poly PP sheet of 3 mm thickness with 4 different size of tools. And these are, for example, the first is with the shoulder diameter 20 mm, next with 15 mm, 10 mm, and 12 mm. So these are the 4 tools that we have used. Then it was observed initially that the initial welding parameter was set at 1000 RPM, speed rate at 0.1 mm per second tilt angle at 0 degree, because tilt angle also, it plays an important role, as I've already mentioned. And welding has been done. And the weld quality was not very much satisfactory as we have observed in these cases. Of course, there are various reasons. I'm not going into more details. And while for testing the quality of the weldment, we have used different standards, test methods, and for the preparation of the specimens also. For example, for microstructural examination, we have gone for STM E20154. For tensile property test, we have gone for D63802A, like this. So these are the different standard test methods and specimen preparations we have maintained. Now, while if we talk about the weldment that is produced by the conventional friction stir welding tool, we have seen that because the heat was not sufficient to soften the material, as I've already mentioned. So what happened? Undeformed material was observed. And as you can see in the figure, that in the figure A, figure B, and figure C, these are the macrographs of the weldments or the specimen. These are welded with the conventional FSW tool, and at different feed rates, of course. And for all the feed rates, it has been seen that undeformed materials are present, because it was not sufficient enough to deform the material, to plasticize material fully. So as you can see also on in the SAM image, that undeformed materials are present and voids and chip formations are there. That is because of the lack of sufficient heat for the welding. Now, so then we came up with the idea of double-sided welding. Double-sided welding means we're using on the both sides of the joint, we have welded with two different pin profiles. Then one is with the 5.5 pin height, another one with the 3.5. First, we have welded, the first pass was done by the 5.5 pin height. Second one was done by the 3.5. Now, what happened initially with the first pass, maximum of the material height, if we talk about throughout the cross section, the material could deform, and subsequently when we went for the double pass, a better weld quality could be obtained in comparison to the conventional tool. However, if we talk in here also, the cracks has been observed, micro voids was present, and a turbulent flow of the material was also observed. So that's why we again thought that maybe this is not again for welding the polypropylene material. Again, we can make it better. So we again thought of developing, and moreover, if we talk about the FTR analysis, FTR analysis from this one, it can be seen that at 1,658 centimeter band, chain breaking phenomenon occurred. So that's why this is one of the reasons why the voids or the cracks took place. And in case of double-sided welding, most of the internal structures remain intact due to high relaxation time, as the local heat input in this case is high in comparison to the conventional welding process. Now here also we can see that with this one, D stands for double-sided and S stands for single one. So we can see that we could at different RPMs we could observe, also we could achieve a better strength of the joint. But again, we again thought for improving the quality of the joint. That's why, and from the fracture tensor, that's why we thought of developing another tool, which is a self-heated tool. And from the fractured tensile specimens and some of the fracture surfaces also, we can see that the failure has taken to that after doing the tensile test, fibrillary structures are present, which indicates ductile mode of failure. So we can conclude from here that double-sided welding can be used to overcome the root defects of the weld joint, which was seen by using the conventional friction stir tool. And the tensile properties of double-sided welding joints are higher compared to the single-sided welded joints, as I've already mentioned. It is comparatively defect-free. but cracks begin on the rotating side of both passes in double side welding. So that's why we thought of developing a tool with additional heating, which will require additional space and supplementary electric energy. It is essential to generate control and moderate heat during welding, which is also very, very important. So first we started our experiment by doing our by considering a milling machine. Then we have developed the tool, and we ultimately, by developing this, we use the main friction stir welding setup. This is the modified tool. So as you can see, the shank will rotate inside the bearing, and with the help of skid rod, we can keep this casing stationary while the tool will rotate. So what will happen when we'll apply load on this brake cable, the frictional shoe will get engaged, and whenever it will get engaged with the shank, what will happen? It will produce, due to the friction that is happening in between the shank and the brake shoes, it will provide an additional heat other than the frictional heat that is generated in between the tool shoulder and the workpiece. So that is an addition. With the help of this frictional additional frictional energy that is happening in between the shank and the brake shoes, we are able to supply additional heat, and that resulted in a sound welding. We have already filed a patent because this has been developed more, and then ultimately we are successful in filing a patent with this one. So if we talk about, we have already discussed about the working principle, because if we talk about this brake cable, so external force was applied by putting loads on the brake cable, and whenever the external force was applied due to the pressure of that is exerted on this brake shoe over this tool shank, so we could produce the frictional energy, and that is how the heat is supplied. So I'll just show you a video. So this shows the conventional FSW tool, but here one of the problem is you can see lots of chip formations are there, as you can see. So that means it indicates material loss. With the help with the conventional tool, there's a higher amount of chip formation, as I already mentioned. This is the modified tool, a novel salvated friction stir welding tool. So here we can see that the chip formation and the material loss is almost negligible, as you can see. There is no chip formation, because that happened because of the additional heat that we could supply.
see any video, only black screen we are able to see.
Yes, sir. What's that?
We could not see any video, only you have shown us only screen, black screen.
Okay. Just let me. I just. Is it visible now? Is it visible now?
No.
Sir, is it visible?
No.
My God.
Okay, leave it. No problem.
So I was saying that whenever we are welding it with the conventional tool, then more chip formation, more material loss is taking place. I just followed the video, and this is what is happening with the conventional tool. With the modified tool. Here we can see that due to the sufficient amount of heat that could be supplied, the chip formation is not there, material mixing is better, and a sound joint we could obtain. So coming back to my presentation again. So if we talk about the average spindle torque versus the traverse speed, we can see that the spindle torque in case of Salvatel FSW tool is more. Why? Because one torque is responsible due to the material deformation that is taking place. Another one is due to the as you can see in the tool, due to the braking action, the spindle torque is higher in comparison to the conventional tools. That's why the average spindle torque is more in case of the Salvatel FSW tool. Okay, and it is around 4.58% higher. So we can say that due to the resistance that is offered by the frictional shoe, the average spindle torque has increased. And it has been seen that as we go on increasing the traverse speed, the average spindle torque increased. That is the reason is due to the less softening of the weld material. Because if we go on increasing the traverse speed, then certainly the heat input to the material will be less, and that's why the less softening of the weld material will take place at higher traverse speed. That's why we can also say that the average spindle torque will increase. And this shows the variation of the Z force and X force. So Z force is basically due to the plunging action of the tool, and X force is the resistance force that is offered by the plasticized material on the tool when it moves ahead. So in the traverse direction. So Z force, these are at different traverse speed. If we see, so we can see that the Z force, both the Z force and the X force are less in case of, because what is our motto? To perform the welding with less energy, right? With less force. So this could be obtained because the material got plasticized very easily due to the additional heat input that we have, that we could be able to supply. So that's why the Z force as well as X force requirement has come down in comparison to the conventional tools. Similarly, we can see that these are the macrographs. These are for the conventional FSW tool, and these are for the Salvatel tool. And we can see that the undeformed material in case of the Salvatel tool is less in comparison to the specimen welded with the conventional tool. So that's why, because the material could, why? Because of the additional heat, more material mixing took place. And that is the reason why those undeformed materials are not present here. Though initially some material loss could be observed, that is due to the additional heat that was supplied, but along with because it depends on the traverse speed also, because how much heat is supplied, that depends on the traverse speed as well as the rotational speed. So as we went on increasing the traverse speed, as we could achieve a better welding joint. Similarly, here also you can see these are the SAM image of the weldment, and here you can see that it indicates laminar flow of the material while mixing took place. So this shows the material loss that took place here. But in the weld nugget, if we talk about here, you can see that the material mixing is uniform and laminar flow of the material took place. That's why it resulted in a good joint. So here also you can see, if we compare, so if we look at the stress strain curve in terms of UTS, 71.4% efficiency was obtained for the salvated FSW tool, whereas when we use the conventional FSW tool for the same material with the same parameters, we could achieve only 51.48% joint efficiency. So with the help of this salvated tool, we could achieve a better joint efficiency. And these are the fractured specimen SAM tractography, which shows ductile mode of failure for the joints. As you can see, though undergraduate students will not understand, but those who are into research and the faculty members who are present, they can easily understand that if there is a fibrillar structure present, then certainly it indicates a ductile mode of failure. So as you can see from the fractured specimens. So these are the conclusions that we can draw from the work. From the FTR analysis, we could see that double-side weld seam exhibited chemical similarity with the base material, whereas the absorption band from the FTR analysis revealed that oxidation occurs during single-side welding. So that's why double-side welding was able to produce a better joint efficiency. And the tensile properties of double-sided welded joints are higher compared to the single-sided welded joints. Use of salve-fitted FSW is able to produce a defect-free welding with the laminar material flow in the steel zone. I've already discussed this. And due to the decrease in the degree of material softening, whatever force we talk about, that is the average Z force, that is the X force, increase with the increase in the traverse speed for both the tools. For salve-fitted FSW tool, the average Z force and average X force increased from 700.2 Newton to 764.98 Newton, and from 739.94 Newton to 793.93 Newton, which is very significant, as you can see, with the increase in the traverse speed. And for the conventional FSW tools also, with the increase in traverse speed, the average Z force and average X force increases. So the highest tensile strength of 16.13 megapascal, that is 71% of the base material, with a maximum elongation of 20.46% was obtained for the specimen that was welded at 0.3 mm per second traverse speed by the salve-fitted tool. These are the references, and thank you. I hope I could finish within time.
Thank you, sir. Thank you so much for your illustrative presentation. I'm sure the engineering fraternity would be benefited from your research work. Thank you, sir. If any questions from the students, faculty members, dignitaries from the dais, or any participants, the dais is open for question hour session.
First of all, if we talk about the defects that is occurring, certainly, as I have shown in the video, that For example, if we talk about I have done research both on laser welding of plastics earlier also. And this is the second time I'm doing welding researches on friction stir welding. Now, certainly in terms of friction stir welding, if we talk about, certainly a good joint, if material loss is there, then that will not result into a good joint, right? So moreover, in friction stir welding, whether the flow that is taking place, material that is taking place, whether it is a laminar one or a turbulent one, that will determine the quality of the welding. Certainly, if we are getting a laminar flow in the material, so that means more uniform mixing will take place. If more uniform mixing will take place, that means certainly the joint strength will be good. So from those things, if material loss is there, because initially only if we talk about, as I've shown in the video also, if material loss is taking place, if chipping is taking place, then certainly it will not result in a sound. So this is how we identify.
Any defect is there, just we use the fusion. It is a confined uniform heating, like based on the thickness, manufacturer is recommending that this much heat is. Simply we put the electrical heat is up. You don't see the what is the how it is happening inside. Simply giant it goes. Yeah, very basic thing. So what I mean to say is, since it is a plastic, is a very low cost and everything, we do not bother much. It is a metallic, we go for the NDT, all those things. So any development is there, that's not in the any technique is there, the wastage of plastic and usage of plastics can be avoided. That is the idea. Anything needs to be, it is a challenge again. Maybe we have to develop.
Because you see, sir, as we have already mentioned, yes, of course, in industries, the way, for example, TNGCL is welding the plastic pipelines, for example. These are the very basic methods, which is practiced. But if we talk about, because we have, why we are doing researches, because if we talk about with the development or the advent of the engineering, so far, if we talk about the development of plastic, nowadays, the engineering plastics are in use. So if we talk about application wise also, they are now even replacing metals in some of the cases. So in such cases, what will happen, we cannot go for these conventional methods. So there should be some reliable method, which will ultimately result in a defect-free welding, a sound welding. So of course, friction stir welding is not the only answer. It depends. For example, if we talk about laser welding, there is a term known as through transmission laser welding, which provides a clear welding. For example, if we join with the help of some heat, say two transparent materials, certainly there will be some joining line that will be visible, right? But with the help of laser, if you weld, if you apply the proper technique, even the joint will not be visible. So those things are already there in the market. So that's why, depending on the material, of course, we say that joining technique, but it also depends on the material, which material I'm going to weld. So choosing the right process for the right material is the key answer. Yes, very much. So thank you, sir.
Thank you all. On behalf of the moderator, I'm summing up the paper presented by our speakers. The first speaker of this session, Engineer Sandeep Kumar Ghosh, the Deputy General Manager, R&D and Project Management, Tata Motors. He briefed us about the latest developments happening in Tata Motors R&D sectors. For years, Tata Motors has consciously worked to embed innovation deep into their organization culture. Today, over 4,500 engineers and scientists are working to push the edges of innovative thinking in the company's R&D centers in India, also in collaboration with UK, South Korea. The impact of this focus on innovation is most evident in the company's expanding portfolio of products. So he has basically given overview of their R&D works going on in and around India. Then our second speaker, Dr. Saurabh Datta, who is Associate Professor in the Department of Mechanical Engineering, NIT Rourkela. He provided an overview on the main additive manufacturing technologies suitable for many engineering applications and other materialistic applications. In fact, nowadays, they have become capable of producing complex net-shaped or net-shaped parts in material that can be directly used as functional parts, including polymers, metal ceramics, and composites. These technologies represent the solution for low volume, high value, and high complex parts and products. He also explained about metamaterials with auxetic cellular structure that have a negative Poisson ratio, which means that when stretched, the material expands in the lateral direction and contracts in the vertical direction. Because it's not a measure of the deformation behavior of a homogeneous solid material, the phrase negative Poisson ratio in most of the deformation behavior of a homogeneous solid material is used. In some circumstances, the negative ratio, Poisson ratio, improves the mechanical qualities for use in engineering, medicine, fashion, sports. This work shows investigation of thermoplast FSW utilizing a newly created self-heated FSW tool, and the findings were compared to those obtained using a traditional FSW tool. The industrial sector is becoming more interested in thermoplastic materials because with high industry to make seats, bumpers, dashboards, fuel system, liquid reservoirs. Research work of Professor Dr. John Debroma is definitely going to be benefit the engineering fraternity. So that's all from the moderator's desk. Thank you. Now, I would like to request Dr. Shubhadeep Bhattacharjee, Honorary Secretary, IEI, Tripura State Center, to propose the vote of thanks.
Good evening to all. I, on behalf of the Institution of Engineers India Tripura State Center, sincerely express gratitude to Engineer A. Anbarasan, Managing Director, Tripura Natural Gas Company Limited, Agartala, who has given his precious time to remain present in this one-day seminar on advances in production engineering as chief guest despite his busy schedule. We also express our thanks to Engineer Vishwajit Deborma, General Manager, Gas Authority of India Limited, Agartala, who is present here today and graced this seminar program as a special guest. We also express our gratitude to Dr. T.M. Gunaraja, past President of the Institution of Engineers India, Dr. Sriram Satyanarayana, Chairman, Production Engineering Division, the Institution of Engineers India, Dr. G. Ranganath, Chairman, Committee for the Advancement of Technology and Engineering, the Institution of Engineers India, who have graced the program today with their kind presence. We also express gratefulness to Department of Mechanical and Production Engineering, NIT Agartala, and Tripura Institute of Technology, Agartala, for their immense support towards organizing this one-day seminar on advances in production engineering in association with the Institution of Engineers India Tripura State Center. We also sincerely acknowledge the guidance and support received from Production Engineering Division Board of the Institution of Engineers India. We are indeed thankful to our distinguished panelists, Mr. Sandip Kumar Ghosh, Deputy General Manager, Research and Development and Project Management, Tata Motors Limited, Dr. Saurabh Datta, Associate Professor, Department of Mechanical Engineering, National Institute of Technology, Rourkela, Dr. John Deborma, Associate Professor, Department of Mechanical Engineering, National Institute of Technology, Agartala, as well as a Joint Secretary of the Institution of Engineers India Tripura State Center, for providing their valuable time for this seminar. We are also obliged to Engineer Chinmoy Devnath, Chairman, the Institution of Engineers India Tripura State Center, and also Chairman of the organizing committee of this seminar program. Engineer Shivashish Bhattacharya, respected member of the Mechanical Engineering Division of the Institution of Engineers India Tripura State Center, and also Joint Secretary Administration of this center. Engineer Sujoy Kaur, Organizing Secretary, Engineer Devashish Poddar, Joint Organizing Secretary, other eminent personalities present either physically or virtually in this one-day seminar program on advances in production engineering. Besides, we are also indebted to all dignitaries, senior engineers, council members of the Institution of Engineers India, officials of the Institution of Engineers India headquarters, past chairmen and past honorary secretaries of the Institution of Engineers India Tripura State Center, corporate members of the Institution of Engineers India, participants from various departments, academic institutes, and stakeholders, and each and every member of the organizing committee and the office staff of the Institution of Engineers India Tripura State Center, whose active involvement and contributions have made it possible to organize this program. We also convey our special thanks to Kingshuk Shed, Assistant Director, the Institution of Engineers India headquarters, for his wholehearted support for organizing this seminar. I also express my sincere thanks to Dr. Sujoy Chakraborty, Assistant Professor, Department of Production Engineering, NIT Agartala, who has given his precious time for this seminar program as moderator. I also convey my sincere thanks to Dr. Suman Dev, convener of the Computer Science and Electronics and Telecommunication Division of the Institution of Engineers India Tripura State Center, who has made necessary arrangement for live streaming of the program from our center. Last but not the least, we convey our special thanks to Dr. Pushparenu Bhattacharya, Assistant Professor in Production Engineering Department, NIT Agartala, who has acted as program coordinator in this seminar. Further, we beg to be excused for any unintended inconvenience caused during the program. Thank you all once again. convey our best wishes for Bengali New Year to all. Jai Hind.